since Stephen is going to tell you what, for those who don't know what dark energy is and what DESI is, etc., I'll just say that this year DESI released the largest ever 3D map of the universe. And mapping something as massive as the universe means managing massive amounts of data. And Stephen is a senior software developer in the lab's physics division who leads DESI's data management team. He has over 3 decades of data management experience, starting with writing a matchmaking app for his high school. I'd like to hear about that. He holds a BS in physics from the University of Washington, a PhD in physics from Harvard University. He did uh, postdoc work at the lab, went to France and came back and has been a staff scientist at the lab since 2010. So welcome, please, Stephen Bailey.
Well, thank you for inviting me to give this talk. I didn't even know this group existed until I was invited, but it's great to be talking to you today. So recognizing that most people on this call are not cosmologists, I wanted to start with a brief history of the universe and how we got to where we're making our maps today. So starting about 14 billion years ago, there was the Big Bang. So the universe basically is exploding, it's expanding outward, and as all the matter in the universe is expanding outward, gravity is pulling it back, slowing down that rate of expansion. Fast forward a few billion years ago, to several thousand years ago, multiple ancient cultures were mapping the stars and the planets, eclipses, things like that. And it was at that time that the Babylonians and the Greeks were establishing the coordinates and the units that we still use. So things like the degree come out of the Babylonians. Our system for measuring the brightness of stars is actually tied to ancient Greek astronomers. And so it's like their choices thousands of years ago are still impacting us today. Most of that work still thought that the Earth was the center of the universe. It was, 400 to 500 years ago that people were realizing that Earth is not actually the center of the universe and that we are, orbiting the sun with our planet. But it's kind of cool to me that as recently as about 100 years ago, astronomers still didn't know whether our galaxy, the Milky Way, was the only galaxy in the universe, or whether there were actually other things out there beyond our own galaxy. They could see these fuzzy blobs in their telescope, but they didn't know if they were small fuzzy blobs inside our own galaxy or whether they were themselves other galaxies. We now know that there are many billions of other galaxies out in the universe. We are just one of them. But that wasn't, realized until about 100 years ago. That was also a time when Einstein was coming up with his theory of general relativity, which was explaining gravity. But at the time, it was generally thought that the universe was static and that just kind of everything was where it was and just kind of hung out there. And he had this great theory of gravity, but didn't have a great theory for like why gravity wasn't just pulling everything in and collapsing and crashing into itself. And so at that time, he added an ad hoc term to his theory that basically pushed back against gravity to keep everything in place. And so he didn't really have an explanation for why that should be there, but he just said, this is what we need to keep everything in place. Shortly after that, Edwin Hubble was observing galaxies and saw that they were moving apart and realized that the universe is actually expanding. And so it was no longer necessary to have something pushing back against gravity, because it was just like if you throw a ball up in the air, it can still be going up while gravity is still pulling it down. And you don't need something to like keep the ball floating in the air. It's just going up and it might eventually come down. Or if you throw it hard enough, it just goes out into outer space. And so shortly after introducing the cosmological constant, 5 years later or so, Einstein ended up dropping the cosmological constant as unnecessary, saying we don't need anything to push back against gravity. Fast forward a few more decades, about 25 years ago, two different teams, one of them with Saul Perlmutter here at the lab, was trying to measure what was called at the time the deceleration parameter, trying to figure out the universe is expanding, but gravity is pulling back. And so the universe must be decelerating under the influence of gravity. And they wanted to be measuring how much is it decelerating? How much is gravity pulling back against the universe versus the energy of it accelerating out, of it going outward? And they were quite surprised to find that the deceleration parameter was negative, i.e., the expansion is actually accelerating. And so there was something that is actually pushing back against gravity. And in fact, in the modern universe, it's actually winning by a factor of about 2 to 1 over what's, gravity is pulling stuff in, and this is pushing it out even faster than gravity is slowing it down. And so we find ourselves in a situation today where about 95% of the universe is stuff we don't understand. I haven't talked about dark matter, but that's something that gravitationally attracts but doesn't emit light, and we can't see it. We can only see its effects gravitationally. Or this dark energy effect, which is the more sort of generic term for whatever it is that's beating out gravity, pushing things apart. And that makes up about 95% of the budget, energy budget of the universe, and we don't understand it. And so what we're doing with DESI and related projects is making maps of the universe, trying to understand how stuff is moving around, where is it, how does gravity interact with dark energy, to try to understand this 95% that we don't understand. And so that's setting the history and context for this map making that we're doing. So the outline for today, I'm going to talk in the first half or so about how we actually make the 3D map of the universe. And then I'll flash some results for how we use that to actually study cosmology, and a few words on where we're going from here. But starting with a tiny slice of the actual map, this was a science as art entry to a recent NERSC competition from a grad student on DESI at Harvard, Claire Lamont. This is 0.1% of the DESI map, and each little point here represents a galaxy that we have measured in our map of the universe. And the Earth is at the center of this here, and then we're looking out. And you can see all of these like big voids where there's not much going on. There's filaments connecting areas that have just tons of galaxies in them. And this here is just a zoom in of the total map that we're seeing. And there are certain directions that we can't see because our own galaxy is in the way, but basically we can look up and down from away from our own galaxy, putting together this map of just like incredible structure in the universe. And so to be making that 3D map, the first thing we do is we make a 2D map of the universe. And this was like while we were building up DESI, we were also taking the observations to make this 2D map, where you basically take pictures of the sky, like this picture in the background. But to get the level of detail that we needed from DESI, we had to combine data from 4 different telescopes on Earth, 2 different satellites that were covered by 6 different funding agencies spread across 4 different continents, plus the telescopes up in space. And I don't know if any of you worked on projects crossing funding agencies, but that's kind of a pain. But we were able to get all of these data collected together. I don't know if anyone is a retiree from NERSC, but NERSC was the place where we brought all of these different data sets together, and having the computers and the data together in one place enabled us to do the joint processing and identify in this version of the map 2.8 billion objects in the map. And most of those objects, these little fuzzy blobs you see here, are not stars in our own galaxy, but they're actually tiny galaxies of their own. And so we can see nice, like big bright galaxies and then some fainter ones, but most of these other little blobs are also galaxies out there, far out in the distance. And so even this just like 2D map of the universe that we prepared for getting ready to do DESI, there's already been 671 papers using these data as of the last time I scraped the archive, looking a little over a month ago. So it's already been a fruitful result just getting ready for DESI. But then if you want some just fun looking at that map, you can go to this legacysurvey.org/viewer. And it's basically like Google Maps for the sky. It's kind of fun. You can zoom in and out and pan around and see different layers of different data sets. And it's just, I loved looking up at the stars as a kid, and now, professionally, I get to do that playing with these data at like the biggest scales, and it's just I still get excited by it. I think it's fun. So legacysurvey.org viewer, it's fun to just see how big our universe is. But the main trick for DESI is going from this 2D map into a 3D map. And so how do we actually go about doing that? So to get the third distance, I'm going to show a plot that was another entry to the Sciences Art Competition for NERSC by another one of our DESI collaborators. And this is tilted on its side so that it can fit on the slide better. But what I'm plotting here is wavelength of light in nanometers on the vertical axis. And then the horizontal axis is look back time for how long ago the light left an object before coming to us. And then each of these different lines is showing a coaddition of what do galaxies look like that come from that long ago that we've observed with DESI. And we co-add all of the data of the spectra of the wavelength versus the height of this is the amount of flux of more light or less light. And you can see that all of the galaxies that are further away, longer distances up to 10 billion years ago, everything is shifted relative to what it is projecting back to today. And so it's this redshift of light that's giving us a proxy for we measure the spectrum and then we look how much is it shifted. This is basically the light version of the Doppler effect of sound, like if a motorcycle or an ambulance is coming towards you, it's higher pitched, and it gets lower pitches going away from you. So we use that, equivalent of Doppler shift of light to measure the third dimension of how far away stuff is. But to actually get those spectra is challenging. So we go back to our 2D map of the universe that we've made, these images, and we pick out some objects that we think are really far away and we want to include in our map, and we identify those. And so then we're going to put a fiber optic cable pointing at that location on the sky. And then we do this for 5,000 locations on the sky simultaneously, and all of those fiber optic cables get run through fiber optic cables and get lined up on a slit all in a line. And then the light shines out of the other end of the fiber optic cable and goes through a grism, basically a fancy prism, and it spreads out the light. And so we have different fibers running in one direction of this and wavelengths running in the other direction. And this is a taste of what the DESI raw data looks like. And most of what we're looking at here, where every fiber has extra light at the same wavelength, that's basically what the night sky background looks like. And so most things are dominated by the brightness of the night sky, not the objects themselves. There's also all these little squiggly things. These are cosmic rays coming in and hitting our detector. We have to mask those out. And then buried in here is the tiny signal of the actual thing we want to be looking at. You can see that some of these are actually brighter objects. These would be like stars we're looking at. Some of them are a little fainter, that might be the actual galaxy we're looking, but there's like slight variations if you sort of subtract off all of those cosmic rays and skies. That's the tiny signal we're trying to find to measure the redshift part and put together this map. And so on the focal plane of DESI that we've mounted on the telescope, there's these 10 sort of pizza wedges that each one has 500 tiny robots. So they add up to 5,000 tiny robots. Here's a zoom in on them. And that right there is the tip of a fiber optic cable being held by a robot. That's about the size of a human hair. And then whenever you go to a new patch of sky, all of these robots can move around where their cable should go to get where a galaxy is at that particular location on the sky. And so these, we have to be lining up something the size of a human hair on this focal plane it's about a meter across, and it gets mounted on our telescope. And so this doesn't look like sort of a cartoon of what we normally think of a telescope being, but up here in this black cylinder, there's the 5,000 robots, and they're all basically looking downward, because here in this white section, there's a mirror. And so at nighttime, this part of the dome opens up, light comes in from the sky, bounces off the mirror, goes up through some lenses, and gets to those 5,000 fibers. And for scale, you can see like this is the size of, a stairway. And so this thing is really, really big. And we're trying to hold these things that are the size of a human hair on a target as the Earth is rotating out from under us. And so the size of that fiber, the Earth is actually rotating by 15 diameters of that fiber every second. And so the telescope is constantly moving, trying to keep up with the Earth rotating out from under us as we're observing the sky. And those fibers get routed off the edge of this telescope and then down into a climate-controlled room where we actually do the measurements. And this is our telescope. I forgot to mention it's at Kitt Peak near Arizona. So that was the biggest telescope on that opening slide that was sitting up on the mountain. And so our nightly operations, we have this telescope at Kitt Peak in Tucson, and every 15 minutes or so, we're getting a new exposure. We transfer that data to NERSC in semi-real time, where we immediately process it, and then we're sending feedback to the observers for, usually that's like if there's some instrument problem, so they get a quick alert that there's something wrong and they need to do something about it. And then we also use it for each day. The survey operations team updates the plan of what else are we going to observe the rest of the survey. So, it could be daily, it could be a couple times a week, but we update, we've observed this part of the sky, we're done with that, we need to move on to another part, or, we didn't get enough signal to noise, we need to observe more. And then also using the supercomputers at NERSC, every year or two, we do a reprocessing of all of the data taken to date. And then that gets fed out to our collaboration worldwide. We're up to almost 1,000 scientists worldwide now that are analyzing this. And we do this 5,000 spectra at a time, every 15 minutes or so, every night for 5 years. And that adds up to tens of millions of spectra that are going into this map that we're building that the collaboration is using to do the science. So timeline-wise, DESI was conceived and led by the LBL Physics Division. We started commissioning in late 2019, but then you might remember what happened in 2020. We got shut down for a while and all went home, and that was disruptive, but we unbuttoned things in late 2020 and started recommissioning the instrument. We had a survey validation phase of just kind of practicing this new instrument and telescope for a while. And then it was in May of 2021 that we started the 5-year survey. So we're in 2024, 3.5 years from now. The first cosmology results that I'll be showing later today, this is based on the year 1 data. But we also have the full 3-year data set in the can, and it's been reprocessed, and we're doing the analysis on that right now, but the analysis is still blinded, so we don't actually know the answer yet on that. But we are on track to finish the 5-year survey early, and as usual with these big projects, you're also always planning the future as well. And so we've put in an application for an extension of DESI and received positive feedback on it, but it's not formally approved yet. This would be using the same instrument, covering more sky area, looking at very similar galaxies for making the map to sort of fill it in both a little bit broader in area and in a little more density, a little more detail. We're also working on what's called DESI 2, where we would be actually upgrading the instrument to get new capabilities that would allow us to observe more distant galaxies and extend the map out further in time. And then there's also plans for something called Spec S5, which would actually be using new telescopes, new instruments, and going even further back in time with still cosmology related, but new science goals for that project, also making maps of the universe. So coming back to this map visualization from Claire Lamont, I've talked a bit about the basics of the 3D map is you start with location on the sky that gets you the first 2 dimensions and the redshift that gets you the distance. But now in the second half of the talk, I'm going to talk some about how we actually turn that into a cosmology measurement. What do we do with this map? Most of my personal work is on the making of the map in the first place, but then that feeds into the 1,000-person collaboration with DESI for analyzing the map to learn things about cosmology. So basics on measuring cosmological distances. I've talked about the redshift of the shift of light, but that's not really a distance per se. That's a how much has the light shifted that gives us a sense of how much the universe is expanding and the how much the galaxies are receding from us. But actually turn that into a proper distance, there's basically two different options. The first option is what's called a luminosity distance that basically says, brighter things are closer. And so to do that, you need something that has a constant brightness so that you know that if it appears brighter to you, it is actually closer, and it's not just that it's fundamentally brighter. But if you have something like a street light where you say, okay, they're all the same brightness, the dim ones in the background, they're further away. Good. This was actually the original method used for detecting the expanding universe, or the acceleration of the expansion of the universe, with Saul Perlmutter and company, with supernovae, which is a type of exploding star that always explodes with the same brightness. What DESI is doing is something I'll go into a little more detail. It's called angular diameter distance, where it's bigger objects are closer to you. And so you need something that you know is a constant size and is actually really, really big, so you can be measuring it on, universe scale things, not even the size of a galaxy. That's too small. You need things that are bigger than galaxies. And we're going to be using something called Baryon acoustic oscillations for doing that. But whether you're working with angular diameter distances or luminosity distances, the connection between the distance that's measured and the redshift that it's measured at is connected by different cosmology parameters. So I'm not going to go through the details of this equation, but it's basically you have distance of some sort as a function of redshift is dependent in this equation on various cosmology parameters that we want to measure. And so, for example, this W that I'll be coming back to is related to the dark energy, this thing that's pushing back against gravity. And so this is a very dense information on this slide, but I'll try to walk through it a little bit slowly. But the very, very early universe, before even stars had formed, it was small, it was very dense, it just had protons and neutrons. So for non-particle physicists, those are baryons. So that's the baryon part of baryon acoustic oscillations. It just had protons and neutrons and electrons flying around, but they hadn't actually formed into stars yet or anything like that. And in that very dense universe, there's like randomly just some places are denser than others. And those denser areas have higher pressure. And so it expands outward from there as sound waves. So it's literally sound waves propagating through the universe when it was that dense. But then at the same time, from the Big Bang, the universe itself is expanding, and sound waves propagate from things banging into each other. I'm talking to you through air banging, against me. But in the universe, it's the protons and neutrons. But when the universe expanded enough that it became not very dense at all, those sound waves basically froze out because there weren't enough protons and neutrons to run into each other to propagate those sound waves anymore. And so this leaves overdensities in shells of a very specific size, which is basically the speed of sound times whatever the age of the universe was at the time it got big enough to freeze out and sound could no longer propagate. And at this time, there were still no stars yet. There's just protons, neutrons, and electrons. But those tiny variations in density that are left over in these shells form the seeds of where galaxies eventually form billions of years later, and then we start observing them now. And so we can measure that size scale by looking at the correlation of the locations of galaxies, that there's a slight excess correlation that galaxies will be separated by a certain distance because of this typical size scale of these overdensities of where galaxies form. And so then we look for that in our maps. We look for these correlations of galaxies are slightly more likely to be a certain distance apart. And the angular scale that appears on the sky, we measure it in degrees across. That angular scale is related to the redshift through cosmology. And then we can use that to study those cosmology parameters. And so this is a plot from the initial detection paper about 20 years ago. So this is looking at the separation distance between two galaxies. And then this is sort of a scaled, basically proportional to the probability that two galaxies would be of a certain distance from each other. And they're more likely to be closer to each other, like gravity's pulling stuff together. But at this specific size scale here, there's this bump in extra probability that galaxies would be at this location distance, not closer, not further. And that's setting the distance scale for this baryon acoustic oscillations. And these different colored curves are different cosmology models fit to the data, showing that some cosmologies are a better fit to the data than others. And so you can see these error bars are big and they're also correlated. And so this was only about a 3 sigma significant effect. But then as we go forward in time with other measurements, that was the original measurement about 20 years ago. About 8 years after that, the same group just kind of, moving forward. DESI was also, LBL was also involved in this one. It's much higher signal to noise. It's, very well established that around 100 in these units, there's a bump of excess probability. And then fast forwarding to today, rather than measuring one bump for like all galaxies over all time, we're now splitting it into, different types of galaxies at different types of distances, where each one of those is individually as good as some of these earlier measurements, like combining their entire data set together. We're now able to split it up in slices of time. And so now we can put those slices of time on what's called a Hubble diagram, where we take the location of that peak and we plot it versus the redshift of how far away are those things in this like shifted light metric. This is, sorry, different units than the previous slide was, but this is basically a measure of where that peak is versus how far away is that peak. And we're looking at, again, different cosmologies fit the data better or not. Down below is the residuals around one of those cosmologies. So you can see our error bars are still pretty big, but we're starting to get into a land where we can be differentiating between these different cosmologies for making the measurements. And so if we're measuring versus the standard model of cosmology, it's called lambda CDM. Lambda was the symbol that Einstein used for this cosmological constant. And then looking at different types of galaxies at different redshifts. Here, we're dividing out by what the standard model would predict. That's the solid line here. And you can see that our measurements are dipping a little bit low at this sort of closer universe. This is looking back in time. We're here at 0, going back to 10 or 11 billion years ago for when the light left those objects and comes back to us. We're getting these baryon acoustic oscillation peaks throughout time. And we see that something might be a little non-standard going on down here. So that's kind of exciting. We're kind of interested in that. If we compare our measurements to prior work, in this plot, the colored dots are measurements from DESI, and the gray dots are basically all of the other experiments combined. And so there's some other experiments in a similar redshift range with similar error bars, but this is like 5 years of their data versus 1 year of DESI data. And this is an analysis only 1 year into a 5-year survey of DESI plus extensions. And so we're starting to make some interesting measurements here. Also, I had mentioned that our analyses are blinded, meaning that we measure the result with an offset that we don't actually know what it is. And so rather than biasing ourselves towards either we expect to be getting the standard model of cosmology, and so you keep debugging until you get that, or you want to get another Nobel Prize by measuring something that isn't the standard model, and so you keep debugging until you get an answer that isn't. We have this offset, so we don't actually know what the answer is until we're done with the analysis, and then we can reveal it. And so we're cautiously excited about these. And then we're also excited that we've got more and more data coming in. And so in the next few slides, I'm going to be turning this into actual cosmology parameters. But just taking a deep breath and a review for a moment of, I realize there's a ton of information going by here for, especially for the non-cosmologists along here, but we're measuring, so these baryon acoustic oscillations that are these leftover sound waves frozen out from expanding universe. So like here I'm showing the droplets of water, and from here you can see that, whatever was dropped here was more recent than over here. But if you imagine that all of them started at the same time, propagated outward to a certain size, and then you suddenly froze it out and then measured everything, that's the size scale we're measuring. And that comes in the excess probability of galaxies being separated by a specific distance. And then we compare that angular size on the sky to what their redshift is to be constraining these cosmology parameters. And so the first measurement we did with this was measuring the cosmological parameters if dark energy was constant in time, which is sort of the form that Einstein thought it was when he first added this ad hoc term. And so on this plot, this is one cosmological parameter that's basically the amount of matter in the universe, how much stuff is normal matter and not, say, light or dark energy. And then versus this dark energy parameter W, where -1 would be the thing that lines up with what would fit sort of Einstein's original version of it. And then the dotted lines here are results from different supernova projects. These are those exploding stars that allow you to measure distances by how bright they are versus how far away they are. This curve is something called the cosmic microwave background, is basically remnant light left over from the Big Bang that you can do other constraints with. And then in blue is the DESI measurements alone. And if you put all of those together, you get this orange ellipse here, which is right on top of -1. And so if dark energy is constant, it's lining up very well with this cosmological constant from Einstein, with about 1/3 of the universe being made out of matter. And so in this fit, we constrain dark energy to be constant in time, but many models predict that it evolves with time. And so if we then say, well, let's split it apart and say we will allow it to, instead of being a constant W that has to be constant across all time, we allow it to vary with time. We then have here W naught is the sort of the constant piece that -1 would be the standard model. And then WA is the amount that it's changing with time. And so 0 would be the standard model of cosmology where it's -1 for the constant piece and it's not changing with time. And if we look at the DESI results combined with this cosmic microwave background or with different supernova samples, all of them are having us be pulled over away from this standard model of cosmology. In our paper releasing this, we showed 3 different contours for these 3 different supernova sets because these sets are produced by different groups, and we as DESI didn't have a, like, we think one of them is more correct than the other. And so rather than play favorites and pick which one, we show it for all of them. Reality is maybe some average of those, but depending on which one of these external data sets we include with, the significance from this point here is 2.5 to 3.9 sigma significance, just on the offset here. The good news is that this DESI year 1 result, it's kind of exciting that we might be measuring something that's not the standard model of cosmology, but it's also completely statistics limited. And we already have our 3-year data set in hand and being processed, or it's already been processed at the time that I'm giving this talk now. And so, I'm cautiously optimistic about this, but I'm going to wait for the year 3 result before getting too excited about, a 2.5 to maybe 4 sigma significance. And so we're still working on the analysis of this. Next month, we have a collaboration meeting where we're going to be unblinding the result to see where the contours are with our 3-year data set. And then we're on track to release the papers at the American Physical Society meeting in March of next year. And so I'm really excited about finding out how these contours are going to evolve. So in summary, I wanted to leave time for questions at the end, some discussion. So DESI is building the world's largest 3D map of the universe. We're doing this with these baryon acoustic oscillations where we're measuring the scale of that versus redshift to measure cosmology. The results from just the first year of a 5-year survey, it's competitive with all prior experiments combined. And there's some interesting hints of non-standard cosmological results, but really want to wait for the year 3 analysis and subsequent that we're on track to release next year. The title of this talk talked about, DESI releasing the map. We actually released just our analysis of the map. The map itself won't be released until at the same time, March of next year. We're going to release the year 1 map while at the same time releasing our year 3 results. This gives especially the younger members of our collaboration more time to work with the map while it's private to our collaboration. But at the same time, we want to give it out to the public for other collaborations and analyses to be working on this. And so we'll be doing this cadence of releasing our latest results along with the previous version of the map. And then we're on track to finish this 5-year survey early, but we're making plans for extensions and upgrades because we're getting these exciting results. We want to keep going. And so if you want to play around with this and learn some more, desi.lbl.gov. This website is primarily for the interested public, though it also has links for scientists and stuff, but it has some links to YouTube videos. At the beginning, I forget whether it was Lynn or somebody or Howard asked me about the 5,000 Eyes. We have a planetarium show that I think is still showing at Chabot once a week called 5,000 Eyes on the Universe. There's also a 2D version of it you can see on YouTube. And then for scientists who actually want to use the data, we do have an early data release that we've released sort of an early, tiny subset of the data for people to play with. But even that tiny subset of the data is large compared to prior projects. And so that's at data.desi.lbl.gov. And so, this is the map we're working on. And I also want to end with thanking you for your interest in this and for listening, and to all of our sponsors. Again, this is led by the Department of Energy, but we also get funding from various other agencies, both in the US and worldwide, to put together this great project spanning the world. Thank you.